Okay, so this is going to be a quick little video on how to do work equivalent loads. So first off, in the simplest scenario, let's say we have a beam of length 2L with a distributed load of Q. Now normally, like what we've learned previously in strengths classes would be that the equivalent of this would simply be a force acting at the midspan with a force equal to this equivalent loading. So that would be Q times 2L, the length time distributed load. But now obviously, if we're doing finite element methods, we only have nodes here and here, and we want the forces at the node specifically. So simply to do that, then we would just take this equivalent load here and divide it between the two nodes. So we would have the two nodes here, the length 2L, and we would have this force divided by 2 at each node. So it would simply just be QL over here and QL over here. That would be the simplest scenario of a work equivalent load, because these two nodal loads here would represent this load here, which would represent this entire distributed loading. But now let's say that we have an extra node here. So in other words, two elements. It's the exact same thing, but now instead of working with the loading between the entire length, we just work with the loading for a single element. So in this case, a single element would be now, with two nodes, it would only be a single length here. And that single element would still have that distributed loading, Q. But now, when you find the total force from that loading, that would simply just be a single QL. And when we divide that between the two nodes, you would get QL over 2 and QL over 2. But because there's two elements, and because they're the same length, they would have the exact same distribution like this. When we combine them together, you would have, let's say this is the one on the left, this would be QL over 2. This would also be QL over 2. But then you'd have the other element here, which has the QL over 2 at the one end, and then it would have another QL over 2. So in this case, you would have, at this end would be QL over 2, here would now be the combination of these. So this would just be a full QL. And here again, QL over 2. And if you add the three of these up together, you would still get a total of Q2L, which is, again, the exact same as we had at the start. Take it a step further, let's think about stresses now. So obviously, in this case where we have a uniaxial stress in the x direction, the stress on this surface here would be quite simple to calculate. It would just be, the stress would be equal to the applied force P divided by the area, which would be 2h times T. But now again, if we were to assess each individual element, which we can see here, there's two elements, and they're both the same size, one element would look like this. I have a height of h and a thickness of t. Now on this element as well, if we were to analyze them separately, they would have to have all the same stresses. That would be the cause from this P. So you would have some force here, let's call that F star, and the stress caused in this element should be the exact same as this stress here, P over 2h times T. But obviously we don't have P acting on this surface, and we don't have the area being 2h times T. What we do have is the force F star acting on the surface area ht. And then we can rearrange that formula to say that this F star, which we can say is like an elemental equivalent of the force. So in other words, if this P were acting on this entire load here to get this stress, this F would have to act across this entire surface area to get the exact same stress. So in this case, the F star would simply be equal to the sigma times the elemental area, ht. But again, normally speaking, when we're doing finite element analysis, we're only interested in the forces at the nodes, whereas this F star acts across the entire surface area. But again, simply just to get the equivalent, just like with the beams from the previous example, all you would do is you would just say that F star divided by 2. because there's two nodes here. So then the force, or the nodal force, would then be equal to F star divided by 2, or a half sigma h t. And that's for one single element. So now if we were to consider, so knowing that the nodal force is equal to a half sigma h t, if we were to consider the full surface area now with the two elements, you would have something like this. Or at least from the side view. Instead of having a P like this, acting on the entire surface area, you would have, for one single element, you'd have F, which is, again, a half sigma ht. And then again, at the other node, F is equal to a half sigma ht. But because there's another element here, which has the exact same forces as the previous element, you would also have an F is equal to a half sigma ht. And there would be another contribution from this element of F is equal to a half sigma ht. And then, of course, you can combine these two loads here at the middle to simply just be 2F, or just sigma ht. And obviously, if you were to add these three forces up, you would be left with 2 sigma ht, which, if we consider the initial scenario, it's the exact same as P, or your overall load, where P would be just sigma times the 2ht. Obviously, this is a very a nice scenario because you have the exact same h values here. But obviously, if these were two different heights, so for example, let's say this was 1 meter while this was 2 meters, they wouldn't be the exact same elements. So you would have to analyze each element individually and find the forces in those two specific elements. But it would be the same thing where that element, or both elements, should have the same stress as the overall stress caused by the total force. And then once you have that stress, you can work out the elemental force and then find from that elemental force, just distribute that between the two nodes. And then just remember that when you have two nodes in common, or when two elements share a node, that node would have a force from both elements, and you would have to add those two together.